Electricity travels through wires to deliver power, but some of that energy is always lost along the way. However, that energy loss doesn't have to happen. Researchers at Penn State have discovered a new method for identifying materials called superconductors, which can transmit electricity with zero resistance, allowing energy to move without any loss. The challenge is that superconductors are difficult to use in most real-world applications because they only function at extremely low temperatures. Such conditions make them impractical for technologies like next-generation energy systems or advanced electronics. Supported by the Theory of Condensed Matter program within the Basic Energy Science Division of the Department of Energy, DOE, the Penn State team has created a new predictive approach that could help scientists discover superconductors capable of working at higher temperatures. According to Zi-Kui Liu, professor of materials science and engineering at Penn State, predicting which materials will become superconductors, especially those that operate at higher temperatures, remains a major scientific challenge. He explained that most researchers still believe existing theories of superconductivity apply only to materials that function at very low temperatures. The goal has always been to raise the temperature at which superconductivity persists, said Liu, who is lead author of a new study published in Superconductor Science and Technology. But first, we need to understand exactly how superconductivity happens, and that is where our work comes in. The BCS theory and the power of electron pairing. For decades, scientists have typically subscribed to the Bardeen-Cooper-Schrieffer BCS theory explaining how conventional superconductors, which operate at very low temperatures, work. The BCS theory says the ability to conduct electricity with absolutely no resistance relies on electron-phonon interactions enabling electrons pairing up, called Cooper pairs, and moving through the material in a coordinated way that avoids collisions with atoms, which means they do not lose energy as heat. Imagine a superhighway just for electrons, Liu explained. If there are too many routes, electrons bump into things and lose energy. But if you create a straight tunnel for them, like the Autobahn in Germany, they can travel fast and freely without resistance. That resistance-free electron flow is what makes superconductors so attractive for real-world applications, Liu said. Without resistance, electrons can flow further with more energy, meaning if scientists can discover new superconducting materials at higher temperatures, it could lead to long-lasting power sources, transforming how we transmit and use electricity. The DOE project aims to understand superconductivity using theoretical tools known as density functional theory, DFT, to differentiate how electrons behave in normal conductors versus in superconductors. The hypothesis is that even though DFT does not explicitly treat the formation of Cooper pairs, the electron density predicted by DFT should resemble that due to Cooper pairs, so that researchers can model how the subatomic particles may behave in a potential superconducting material. Until now, the BCS theory based on the formation of Cooper pairs and DFT predictions based on quantum mechanics have remained separate. Liu's team found a way to connect them. The key to the discovery, the researchers said, is a concept closely related to what is called zentropy theory. Zentropy theory combines ideas from statistical mechanics, which is the study of how large groups of particles behave, with quantum physics and modern computer modeling. Zentropy theory helps explain how the electronic structures of a material affect its properties as temperature changes, which in turn affects when it changes from a superconductor to a non-superconductor. However, zentropy theory requires understanding and prediction of the superconducting configuration of a material at 0 Kelvin, the coldest temperature possible, also called absolute zero, where all motion of atoms and molecules stops. Liu's team showed that even DFT, a popular computational method not originally designed for studying superconductivity, can reveal important clues about when and how this phenomenon occurs. predicting new superconductors. This approach is especially valuable because it offers a new approach to predict whether a material is a superconductor or not, and the entropy theory can then be used to predict the transition temperature from superconducting to non-superconducting, Liu said. The BCS theory works well only for superconductors with very low transition temperatures, since the Cooper pairs are easily destroyed at high temperatures, and currently there is no theory for high-temperature superconductors. Through the DFT predictions, Liu's team found that the resistant free electron superhighway in high-temperature superconductor is protected by a unique atomic structure resembling a pontoon bridge in rough water, so the superhighway can be maintained at higher temperatures predicted by the BCS theory. The team used this method to successfully predict signs of superconductivity in materials including both conventional superconductors explainable by the BCS theory and the high-temperature superconductor, which is believed to be unexplainable by the BCS theory. The team further predicted the superconductivity in copper, silver and gold, which are not usually considered superconductors, probably due to their ultra-low temperatures. This new capability could help uncover new and superconducting materials at higher temperatures, according to Liu. The researchers' next steps are twofold. One is to apply this new method to predict the transition temperature from superconducting to non-superconducting as a function of pressure using the entropy theory in existing high-temperature superconductors, and the other is to search for new superconductors with higher transition temperatures through a comprehensive database with 5 million materials that the team has been building. The team would like to identify potential candidates with the right properties for superconductivity and work with experimental scientists to test the most promising ones. "We are not just explaining what is already known," Liu said. "We are building a framework to discover something entirely new." If successful, the approach could lead to the discovery of high-temperature superconductors that work in practical settings, potentially even at room temperature if they exist. That kind of breakthrough could have an enormous impact on modern technology and energy systems.